d x comma y. This is the goal, right? But I have some training data. From that data, I want to learn the pattern, in this case, the mapping. And then if you give me a new input, I should be able to predict corresponding to that input. That is the objective. This in mathematical terms, how does it look? This corresponds to the predictive distribution. This is what we want to find out, right? And this is equal to integration probability of y star given x star comma theta, not d, given theta multiplied by probability of theta given the data, and then you integrate out all the theta, right? We have seen this earlier. The first time we saw it was for, I think, coin tossing example, and since then we have been seeing this again and again. Now, and this is the ultimate goal, that I want to predict y star given x star, and since it is probabilistic machine learning, I will get distribution of y given x, the PDF of y given x, right? Now, what is the bottleneck in this thing? The bottleneck is probability of theta given d is not known to me, and that is to be computed. So, however, to use or to predict or to obtain the predictive distribution, the posterior first needs to be computed. The posterior is probability of theta given d. So, we have to compute the posterior if I have to make the predictions. Okay. So, however, to obtain the predictive distribution, posterior probability of theta given d is to be computed. Okay. And now you remind me, how do you compute the posterior? What do you use? The Bayes law. That's why it's Bayesian. So, and we compute it as theta given d is equal to probability of theta, which is my prior, multiplied by probability of data given theta, which is my likelihood, divided by probability of d, right? But then computing posterior itself is the bottleneck, because this is intractable. You cannot compute this in 99.99% cases, because the denominator is intractable. So, however, the posterior, which is theta given d, is intractable as probability of d is intractable. In almost all cases. The only exception is the conjugate prior, but in almost all cases. Okay. So, yes, with conjugate prior, then you can compute probability of d by looking at the unnormalized one. That will take the form of Gaussian. So, probability of d should be the normalizing constant of Gaussian. But otherwise, this is generally intractable, right? And that becomes the bottleneck. And whatever we do is to address this bottleneck. And in our discussion on addressing this bottleneck, we have till now discussed about sampling based approach, which addresses this by drawing samples that represent the posterior. And for drawing samples, you do not require the normalizing constant. Knowing a distribution up to the normalizing constant is enough, right? So, unnormalized distribution is enough. So, we have discussed different sampling algorithms to address this. However, sampling based approaches are slow, okay, or computationally expensive. However, sampling based approaches are computationally expensive. Okay. And this is particularly true for when theta is very high dimensional. Okay, this is particularly true when theta is in the order of, I don't know, millions or trillions, something like that we are talking about. Okay. So, one group of algorithms that address this is the approximate inference algorithm. So, approximate inference algorithms attempt to accelerate this accelerate computation of probability of theta given d. Let's go sen of probability of theta given d. Okay. So that is what the idea is. We want to do inference in a rapid manner. We want to do inference in an accelerated manner, so that we can actually tackle or we can actually scale to high dimension. Okay. But this computational cost, nothing is free, so this computational cost does not come for free. There is a cost for that, and what is the cost? It's there in the name, accuracy. Because remember, for sampling method, you could guarantee that if you draw infinite number of samples, or if n is very large, those samples represent the distribution exactly. That was guaranteed. But in this case, there is no such guarantee, because we are starting with the idea that we are going to approximate it with some tractable distribution. So we will approximate the posterior with some distribution which is tractable, with which we can work. And one example of tractable distribution is Gaussian, but it need not be always Gaussian, it may be some other kind of approximation. Okay. So this is the idea, and this is achieved. This is achieved by imposing certain assumptions. Okay. / approximations, and that justifies the name. Okay. Now we will be talking about algorithms, and you will realize that different algorithm has different assumptions and approximation. But just to give you some idea what kind of assumptions and approximations we are talking about, one of the assumption can be, let us approximate it as a Gaussian, the most easiest and trivial kind of approximation. The other can be, okay, we will not approximate or not talk about the distribution as such, but can we impose conditional independence or independence? So these are the kind of assumptions we will be doing. So when I say assumptions and approximation, that means that you will either assume a family of distribution, Gaussian for example, that is one way of doing things. The other way of doing things is that, okay, we will not approximate something like that, but you will put some very strong assumptions or approximations on the distribution itself. For example, that these thetas are independent. If you assume the theta is to be independent, it becomes product of one-dimensional Gaussians or one-dimensional distributions. And then with that, can our life be easier? So these are the kind of assumptions and approximations we will see. So approximations include considering a tractable distribution, example is Gaussian, or imposing independence. These are just two ways, there can be other ways also, okay? But these are just two ways that I want to highlight. Okay. So now let us introduce some definitions that we will be needing in the context of approximate inference. Okay. Some definitions. So some definitions, and with these definitions we will formalize the problem. So the first thing we will define is the target distribution, the same name I am using from before, distribution, and this is denoted as pi, that is what I was using earlier. So we will use the same thing to avoid confusion. So target distribution is pi of theta, which is probability of theta given d, right? Pi of theta is a target distribution. Target means the distribution that I want to approximate. Okay, target means the distribution which is intractable and is needed, and I want to approximate it. Clear? Which is equal to probability of theta, probability of d given theta by probability of d. We can write it as pi star theta divided by z pi. What is pi star theta? We have been using it. What is the pi star notation? That no numerator, the unnormalized distribution. What is z pi? The normalizing constant. Okay. Why am I writing it in this manner? Because at some stage we have to keep in mind, at every stage actually, that probability of d cannot be computed, that is to be avoided. If at any stage you find something where probability of d is to be evaluated, you are in trouble. So that is to be avoided. So that is why. Okay. But the thing that I want you to remember is that target distribution is pi theta, which is our posterior always in the machine learning context, and which can be represented as unnormalized by the normalizing constant. Clear? Okay. The second thing which is new is the surrogate distribution. Surrogate distribution. Okay. What is the surrogate distribution? This is the distribution with which you want to approximate the target distribution. So this is the replacement. Surrogate means replacement. So this is the replacement distribution. So this is the distribution with which the target distribution will be approximated. Okay. So this is the distribution with which pi theta will be approximated or represented, whatever you want to call it. Okay. And this we will denote as the same notation as the proposal q of theta. Okay. So this we will be denoting as q of theta. Okay. This is denoted as q of theta. Okay, clear? Any questions? No? Okay. So if there is no questions, then can you tell me that what is my ultimate goal with this setup? What is the aim now in approximate inference? What is the aim? When will you say that you have a very good q theta? When will you say that? Or rather, what is the broad high level question is, what is the aim in approximate inference? What do you think is the aim, rather, I should say? Not pi theta minus q theta, but you are correct that these two distributions should be as similar as possible. Make q theta as similar as possible to pi theta, right? Or minimize some distance metric between these two distribution, right? So the aim is minimize some distance metric between pi theta and q theta. That is what you will want to do, correct? Clear? Now, what is pi theta? What kind of quantity is pi theta? It is target, but what kind of quantity is this? Is distribution, it's a PDF, right? What is q theta? Distribution. So your metric, what should it measure? Difference between two distribution. Do you know any metric that measures KL divergence? So we did talk about KL divergence very briefly, and I said that that is a metric that measures distance between two distribution. So that metric, some distance metric will be our KL divergence, but it can be some other metric also. There are other metrics also, but most popular one is KL divergence, and most of the development till now is based on KL divergence because of certain properties it has. Okay. So this sum distance metric is basically my, so we use KL divergence. Okay. KL divergence is a known distance metric that measures difference between two distributions, correct? What is the full form of KL divergence? Kullback-Leibler. I confuse it with Karuban-Loeb. That's an expansion, this is a distribution. Okay. Kullback-Leibler divergence, but that is not needed. Remind me, what is the KL divergence formula? So I want to find KL divergence between pi of theta and q of theta. Can you remind me what is the formula? We wrote two formula, one in summation form, one in integration form. We will use the integration form because for us everything is continuous. So what is the formula? KLPQ, it is equal to expectation or integration of P log P by Q. So this is equal to integration of pi theta log pi theta by q theta d theta, and we will integrate over the domain of theta, right? Clear? Do you see any problem? Okay, now what is this quantity is equal to? What kind of statistical quantity it is? Expectation of log pi by q. So this is equal to expectation with respect to what? Pi log pi theta by q theta. Now, do you see any problem with this expression? I mean, this expression is correct, but do you see any problem with using this expression? I mean, for using any metric, right, that metric should be, you should be able to evaluate that metric, correct? Can you evaluate this metric? Why? Pi theta is unknown. More importantly, the expectation is with respect to pi theta, where pi theta itself is unknown. So, you cannot use this. Actually, you can, but that we will not discuss today. There is one algorithm known as expectation propagation algorithm, which is an approximate inference, and that uses this. But that obviously under some assumptions and approximations, but that we will not discuss today. Okay. So, for now we will say that this is difficult to use because the expectation is with respect to pi. Okay. So, it's problematic as the expectation is with respect to pi. What is the solution? Suggest the solution. What can we do to use this? Can you think of some alternative metric? Clearly, this metric we cannot use, at least for today we cannot use. So, can you think of some alternative metric? Repeat. Multiply and divide by q of theta will not help, because then also you have to sample, and sampling is not, see, I said this you cannot evaluate, but you can, I mean, if you want to do sampling, then you can draw samples of pi. The whole point is not to sample. So, what you are suggesting is the important sampling route, which is a good suggestion, but we don't want to sample. So, we cannot go that route, right? So, anything else? It is very simple. Is scale divergence symmetric? So, then can I not use q given p, or not given but q and p instead of p and q? What will happen if I do q and p? The expectation will now be with respect to q, which is my tractable distribution. So, things will become simpler. So, that is known as reverse scale. So, therefore, because it is problematic, we use reverse scale. So, we can use reverse scale, which is scale between q theta and pi theta, which is equal to integration of q theta log q theta by pi theta d theta. Right? And this is something we can work with, or can we? Can we work with this also, or do you see any problem here as well? We don't know z pi. In other words, we don't know pi theta itself. But first of all, we know pi star theta. So, what we can do at least is write pi theta in terms of pi star theta and z pi. So, this is equal to integration capital theta. I am going to omit this capital theta from next step, but it is there, but I will not just not write it. So, log q theta dot z pi multiplied by z pi by pi star theta d theta. Okay, clear? Now, this is equal to, the problematic part is z pi, right? So, I am going to separate it out. So, I will have one term without z pi and one term with z pi. Obviously q theta I cannot eliminate, q theta will be there. So this is equal to integration q theta log q theta by pi star theta, right, plus d theta plus theta q theta log of z pi d theta plus, right, yeah, this is correct. What is the first term? First term is what is the first term? Expectation, correct, but something else? Isn't that KL divergence? That is KL divergence between Q and the unnormalized. So the first term is equal to KL between Q and, I am not writing theta, pi star. Now the interesting question, what is the second term equal to? Let us see, you can say. It is easy, but just you have to be little aware, I will say. What is this equal to? You have to do some mental maths. That is another clue. Yeah, repeat. Log z pi. Why? Log z pi is a constant. It's just not a function of theta. It will come outside, and then it's a distribution. So integration of q theta d theta is equal to 1. So this is equal to log z pi. I will anyways write that what I said just now, but the second term is going to come out as log z pi. Okay. So which is equal to KL between q theta and pi star theta plus log z pi integration of q theta d theta, and this is equal to 1, because that is a distribution. If you integrate over all theta, it will give you 1. That is the property. So then therefore you have KL between q theta and pi theta is equal to KL between q theta and pi star theta plus log of probability of d, so that is z pi. Z pi is probability of d, okay. So that is evidence, remember that name, okay, or rather now it is log evidence, right, okay. So we got this, right. Now what can you say about log of z pi? What is that? If you change q, because remember, okay, let me put it this way, pi, can you change it? Are you allowed to change pi? No, that is what you want to approximate. So pi is fixed, okay. Obviously pi changes with theta, but pi as a distribution is fixed. So if pi is fixed, what about q? Can you change q? Yes, q is what you are trying to adjust. So q you can change. Now if pi is fixed, what about z pi? It has to be a constant. So if the target is fixed, its normalizing constant is a constant, correct? So this term will never change. If you change q, the left hand side term will change, the right hand first term will change, but the right hand second term is a constant, correct? Because it is a constant, we let us take it to the left hand side and bring everything else to the right hand side. So it will become constant is equal to something plus something, okay. So this implies log of z pi is equal to minus KL q theta and pi star theta plus KL q theta and pi theta. Clear? Right? Now, can you tell me the expression of minus KL q theta by pi star theta? What will change in the KL divergence expression for a minus sign? The log will swap, I mean, right? That is the only change you will get. So, instead of q log q by p, we will get log q log pi by q. That is the only change, right? Keep that in mind. Okay. So, finally, this implies log of z pi is equal to that minus of KL, the first term, I am going to call it L. L of q, because q is what is allowed to change. Okay, theta anyways is the range, but q is what is allowed to change in this case, plus KL q and pi. Clear? Any doubt on this equation? Where? Let me write LQ also. LQ is equal to minus KL q and pi star, which is equal to integration q theta log pi star theta by q theta d theta. Right? Clear? So, this is the quantities I have derived. Okay. So, now let us try to look at a diagram. So, suppose this is my some reference frame. Okay. Okay. From here I am going to measure the distance. You can think of it as an axis also. Okay. And in y axis I am going to measure. So, first let us talk about log of z pi. Log of z pi will be at a certain height and that is constant. That means you cannot change it, it is fixed, right. So, let us say this is my, let us call it log of z pi. Okay. Clear? The second thing you have is KL divergence between q and pi, the right hand side term. What is that equal to? What is KL q pi is equal to from that expression, from equation 1, let us call it equation 1. So, you have to take one term to the right hand side. What will it be equal to? KL of q and pi is equal to log of z pi minus L of q. So, now let us say this is my L of q. Okay. So, L of q actually I am measuring from here and log of z pi also I am measuring from here. Now, in the diagram can you tell me what is KL, q and p? Some other color I want, green. So, now from in the diagram what is KL between q and pi? It is the difference between log of z pi and L of q. So, the difference between the two lines is my KL divergence. So, this is equal to my KL q and pi. Okay. Clear? Now what do you want your KL between Q and pi to be? What is the ideal value of KL, Q and pi? 0. Remember KL divergence is always greater than or equal to 0. Okay. And you want it to be 0. Correct? When KL, Q and pi is equal to 0, what can you say about this sky line and this violet line? They will coincide. Correct? So if you want to minimize KL, Q and pi, what are you trying to do? Maximize L of Q. Correct? So L of Q is known as the lower bound of KL, Q and pi. And you want to maximize that. Right? You want to maximize the lower bound. And if you can actually maximize it to the global maxima, in that case, KL, Q and pi will go to 0. And why is L of Q important? Why is L of Q important? Because you have to remember we cannot work with KL, Q and pi because pi is not known. But we can work with L of Q because L of Q is involving only pi star. So instead of working with KL, Q and pi, which is to be minimized, which we cannot because pi is not known, we can work with the L of Q, which is negative of KL of Q and pi star. And pi star is known to us. And we can try to maximize that. Negative will maximize, positive will minimize. Okay? Clear? So, this is the quantity we try to maximize this or maximizing LQ is equivalent to minimizing KL, Q and pi. Clear? Any doubt? So, if this is clear, then what is my problem statement then? The problem statement is give me the Q that maximizes L of Q. Okay. So, therefore, the problem statement is Q star is equal to arg max Q L of Q. Okay. Clear the problem statement? Now remind me what is Q? Approximate what? Distribution. What do you mean by distribution? I want a full name. What is Q? What is Gaussian, uniform? What are this? PDF. What is the full form of PDF? Density, not distribution. Distribution means CDF. But anyways, that's not a point. The important word is function here. So Q is what? It's a function. So what are you optimizing over? Function. So if I have to optimize it, I have to take derivative with respect to function. That means we are using variational calculus. What is variational calculus? You have a function of function, right? Output might be a scalar, or that's okay, but it's a function of function. And you are working with variational calculus. So that's why this inference is known as variational inference. So the name variational inference comes from the fact that you have to use variational calculus because you are operating over function. You are trying to find the function that will maximize or minimize some loss. Okay. So that's why this whole method is known as the variational inference. Okay. So Q is basically probability density function, which means we are working with functions and functionals. right? Which means we have to use variational calculus, and that's why this group of method is known as variational inference, which means we have to use variational calculus, and therefore this method is called variational inference or VI. VI is also a popular name. Okay. That's why this is known as variational inference. Okay. So this is the broad framework, by the way. This is not any method. This is the broad framework. We will be talking about one method now, but this is like the foundation. So this is like drawing samples. Now, once you know how to draw samples, you can use it for importance sampling, metropolis thing, Hamiltonian Monte Carlo. But first we discussed about drawing samples. So this is that part. This is the foundation. And this, on top of this foundation, you can now build mean field approximation, which we'll discuss next. You can have expectation propagation, which will change slightly because I will use the forward, but that's another method. So everything is built on top of this discussion. Okay. So now, with this setup, let us talk about one of the method, which is the mean field method or mean field approximation. Okay. Mean field approximation. Okay. This is known as the mean field approximation. So what did I say, that how the different variational inference or approximate inference algorithms differ from one another? How think about two approximate inference algorithms. Now, what do you think will change between these two algorithms? The way you assume Q or the assumptions you are imposing on Q, that might result in different algorithms. Also, whether you are using the forward or backward KL divergence can also result in different algorithms. Okay. So, in mean field approximation method, by the way, this is kind of motivated again from statistical mechanics, although we will not need statistical mechanics for discussing this, but this is motivated from there. So, in mean field approximation, what we approximate is that the Q theta, the surrogate distribution, is fully factorized, which means that the parameters are independent. That is the basic assumption that it works with. Okay. So, oh, by the way, one thing I forgot, because this inference is known as variational inference, Q theta is also known as the variational distribution. So, the surrogate distribution is also known as the variational distribution. Take a note of that, because that is the more popular name. Surrogate distribution you will not find in the book. That I was using because I had not introduced what is variational inference. So, generally you will see that Q theta is known as the variational distribution, because that means that is the distribution on which you will use variational calculus. Clear? So, that I don't, you write it down, I am not writing here. Okay. So, now in mean field method or approximation, we assume that the variational, so I am now using this name, distribution, and since it is the first time I am using it, I will also write also known as surrogate distribution. So, that will clarify it. Distribution is fully factorized. Okay. What does it mean? It means that your q of theta can be written or decomposed as I equal to 1 to capital K qi theta I. This is what it means. Can you tell me what else does it mean? I told it actually little while ago. It basically means that all the thetas are independent. They may not be identically distributed, but they are definitely independent. Now, if theta is also identically distributed, then what will change in this? So, this expression only assumes independence. It does not assume identically distributed. So, just to make things clear, just to let us assume that it is also identically distributed. Then what will change in this equation? Can you tell me? Qi will, it will be fixed, so it will be q, it will become q theta I or q bar theta I, something like that. So, q will, now q is also changing with I and theta, right? In that case it will not be qi, because then the distribution is identical. So, for any I you will get the same distribution. Now the distribution is changing with I, so it is qi, clear? This fully factorized means independence assumption. Okay, clear? Okay. So, now this is the first thing we do in mean field approximation. The second thing we do is we update or compute one q at a time. Okay. So, in mean field, one qi is computed or updated because it will be through some optimization, updated at a time. Okay. So, you will not update all the q together. You will assume or keep other q's at their previous location and select one and update that. Next you will keep fixed, update the next one, and this will go in a loop. In a for loop you can think about it, where you iterate over each q at a time and update that, while keeping other q's fixed. Clear? So, now with this setup, let us consider the jth update step or jth component getting updated, something like that. Okay. So, at jth update step, what will be my loss function? LQ. By the way, LQ has a name. LQ, what is LQ? It is the lower bound of the evidence. So, it's so that not the of the evidence, but using the evidence, right, or of the evidence. So, LQ is the lower bound of the evidence. You follow or not? Because think about that line, that is the minimum it can. So, elbow is the method that it is known as the elbow optimization, which stands for evidence lower bound optimization. So, this, where is that? This, right? This thing is known as elbow. Evidence lower bound optimization. Okay. Because you are working with, that is the lower bound of the evidence and you are optimizing it. Okay. So, now, so what will be the elbow loss in this case? If it is the jth update, take a look, you can have a look at your notes and tell me what will be the loss. First of all, it will be L of Qj, because I am only updating the jth one, others are keeping fixed, right? Now, what will be the loss? What will be it look like? This is equal to integration of product I equal to 1 to k qi theta I log, it is opposite, so pi star will go up, theta by product I equal to 1 to k qi theta I d theta. Correct? So now remember that I am only interested in the jth component. So what will I do? I will separate out the jth component from the remaining k minus 1 component, right? That is what I will do. So this is equal to integration, this pi I will write it as q of j theta j, and then product I not equal to j q of I theta I, right? Clear? Similarly, log pi star theta by q of j theta j product of I not equal to j q of I theta I d theta. Correct? Now, what am I going to do is that there is a numerator, there is a denominator in the log term. I will separate log a minus log b, and I will come up with two terms, one corresponding to log a, one corresponding to log b. Okay. So what is the first term that I will come up with? Tell me. It will be equal to integration of q j theta j, first term, theta j. I want to make my life simpler. So what I will do is, this term I will call it q minus j theta minus j. What does it mean? It includes all the theta, product of all the qi theta I except I equal to j. That is the notation I am using. Okay. Same will happen here also. This will become q minus j theta of minus j. Okay. This fundamentally means q1 theta 1, q2 theta 2, qj minus 1 theta j minus 1, qj plus 1 theta j plus 1. So the j I will skip, and then it will go up to k. So only the jth one will not be there. If it is 1, 2, 3 and it is j equal to 2, it will be 1 multiplied by 3. The 2 I will skip. Okay. So okay, so then the second term will become q minus j theta minus j, and then log of pi star theta d theta, right? This is the first term. What is the second term? Minus integration qj theta j q of minus j theta j, and then you have log of product. Log of product is equal to summation of log, correct? So the set summation I will bring outside. So you will have log of qj theta j, right, plus summation over I not equal to j log of qi theta I. I did not write that notation, but that's okay, I guess. D theta. Any doubt? Straightforward, right? Now, this integration you see, what is the dimensionality of the integration? Is it one integration, two integration? How many integration are those? Any one term? How many integration? Because you are integrating theta, k dimensional. So these are actually k dimensional integration, because you have to integrate on each theta. So I will again separate that integration into 1 and k minus 1, jth and everything except jth. So this is equal to then, this is equal to integration over the theta j, qj theta j, then integration over theta minus j. You have q of minus j theta of minus j log of pi star theta d theta not theta, d theta minus j, and then d theta j. Theta minus j is a vector, theta j is a scalar. When I say minus j, it becomes vector of one dimensional list, that is all, whereas j is a scalar. Okay, theta j. Clear? There is one more term, the second term. The second term is easily decomposed into two terms because I will that summation is there, right? So the second term I will decompose into two terms. So minus, what will be the first term? Integration of qj theta j, then q of minus j theta j, minus j theta of minus j, sorry, log of qj theta j, right? Yeah, qj theta j, and this is over all theta right now at least, minus the last term is equal to integration over theta qj theta j, q minus j theta minus j, log of or summation of log, actually summation of, yeah, summation is there. So summation over I not equal to j q of qi log qi, sorry, please let me know if you spot any mistake because I am writing it without going back to the previous slide. Log of qi theta I t theta. Okay, the expression is correct. If there is any mistake, please point it out. Okay. 1 second, Subhankar, attendance. Okay. So now there are three terms. We will work with one term at a time. Let's work with the first term. In the first term, can you tell me, green, this integration, right? What will be the outcome of this integration? I don't want the answer, but what will it be function of? Some law. Only theta j. Some law. Whatever you integrate out, that is no longer a function of that. So you have already integrated out theta j, theta minus j. So what is remaining is only theta j. So that will be a some function of theta j. I will call it log of f theta j or fj theta j. Okay. So with that understanding, this is then equal to integration of qj theta j log of fj theta j, and this log function is basically that integration. Okay, d of theta j, right? This is what this is based on the understanding that this integration will only function of theta j. Let's assume that is log of f theta j. That's, I am assuming that to compress it. Clear? Second term, the black one. Okay, so let us see. So this is a k dimensional integration, right? I will separate it out, keep this and this together and this separate. Clear what I said? So this will give me minus integration qj theta j log qj theta j d theta j, okay, multiplied by, I am writing here, multiplied by integration q of minus j theta of minus j d of theta minus j, right? Because it is already separable based on my assumption, so I have separated out. Tell me what is the second bracket equal to? The bottom line, what is it equal to? What is q of minus j? 1, that is correct, because q of minus j theta j is basically the joint distribution of all the variable except the jth variable. That is a PDF, valid PDF. So you will integrate it out, you will get 1. I will repeat, q of minus j theta of minus j is the joint distribution of all the theta except the jth theta. Q of minus j theta of minus j is joint distribution of all the theta except the jth theta. Obviously variational, but that is okay, it is still a distribution. So if you integrate it out, it is a joint distribution. Integration of a joint distribution is equal to, any distribution is equal to 1. So this term will go to 1. This will be equal to 1. Okay. The last term, what will be it equal to? Last term is in sky. I will write it in the next slide, but first of all let us see. So again, last term is qj theta j, that is only function of theta j, and then the remaining term is function of everything apart from theta j. If I integrate it out, what will I get? No. First tell me what will happen to theta j integration. 1, right? And there will be remaining term. Will that be a function of theta qj? So that is like a constant. So this term is going to be a constant. That means it is not going to be a function of qj. So let me write it down, minus, and then I will write it in the next slide, integration of qj theta j d of theta j, and then integration of q of minus j theta of minus j summation I not equal to j qi theta I d theta minus j. Correct? This is the expression, and as correctly pointed out by you, this is equal to 1 and this portion is not a function of theta j, so which means it is equivalent to constant. Clear? So what are you finally getting after all of this? So this finally is equal to the last line, integration of qj theta j log of fj. You might not write j, fj, as long as there is theta j you are fine, okay, but I am writing it, okay, minus integration of qj theta j log of qj theta j d theta j, plus or minus whatever you want to write, actually minus, so let us write minus, it will be useful for me, minus some constant, okay, clear? So now what is this expression? I did so much math, but what is this equation equal to? What were we trying to deduce? L of q, right? And what do we want to do with L of q? Maximize or minimize, something like that, right? So what do you think you will get if you try to maximize or minimize this L of q? What will you get? You either want to minimize L of q or maximize L of q or minimize L of minus q, right? So what do you think you will get if you do this as q of j? Q of j is what you want to find out. What will be the value of q of j? Try it out yourself, okay? I'm giving you the answer. See, there is log and log. So you can combine the two terms. It will become integration of qj log fj by qj. This is what you want to maximize. So that means if you take a negative sign, that is what you want to minimize. Correct? So what do you want to minimize? qj log qj by fj. That's what you want to minimize. What is that equal to? Scale divergence. When is scale divergence minimized? When log term is equal to 0. That means log, the numerator and denominator will have to be equal to same. So your qj will come out log of qj, that qj theta j will come out to be fj theta j. Right? There is one catch here, there is a constant term here. So you have to treat that constant term as a normalizing constant and put it inside that log. So you will get qj is equal to fj divided by the constant. And what is fj? Fj is, log of fj is actually this term. Where is that? I wrote somewhere, right? Yeah, that term. This term, right? The green one. What is that equal to? That is equal to, if you think about it, that is log of fj. So fj is equal to exponential of log of fj. So you can add an exponential to that. So just to complete the things, you will do it, but I will give you the answer. So by maximizing, you will get, or we will get qj theta j is equal to, as I said, exponential of log of fj theta j divided by some constant z, which will come from the constant term, which will act as a normalizing constant. Okay, and this will be equal to 1 by z, let us keep as it is, exponential of, now tell me what is this integration, log of fj, what is it from our definition? Integration over q of minus j theta of minus j log pi star theta d theta minus j. Correct? That's the definition. Now you tell me what is that integration in expectation form. What is that integration? 1 by z exponential of expectation with respect to q of minus j log of pi star theta. Right? So what are you doing here inside the bracket? You are taking expectation, the mean of the unnormalized distribution. Correct? While considering every other q to be fixed. Correct? That's why the name mean field approximation, because you are taking mean of the target to arrive at q. That's why the name mean field approximation. This you should prove yourself. Okay, should not be more than 2 lines. Okay, I already told you that just combine the two, take the reverse of that, that will be negative sign that you want to minimize, and log is minimized. So just do that, you will get it. Okay. So again, I will repeat. This method is known as mean field because you have a mean here. So, this justifies the name. Okay. Now, think of the algorithm. You will first assume some q and then you will go to each q and update it. Like that, you will go to q1, q2, q3 dot 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 qk. After qk, you will not stop, you will go back q1, q2, qk, and like that you will iterate until convergence. Okay. So, algorithm wise you will initiate some q and then go on optimizing or iterating over those while updating one at a time. Clear? Any doubt? So, if there is no doubt, I will stop here. And next class is, so next class will not be there. Thursday there is no lecture, I am not here. So, that means we will meet after your midterm break, right? Which is on 14th if I am not wrong. Probably, okay. And on that day, we will have one more lecture on approximate inference, which will be the expectation propagation. And after that, we will start Gaussian process. So, in the next lecture, we will be done with the algorithm part, because sampling is done, approximate will be done, and then we will look into specific machine learning algorithms, and there we will again find application of this, and we will start with Gaussian process. Okay, clear? Thank you.